Hello and welcome to the Sleepy Oceanographer. If you are looking for somewhere quiet to rest your thoughts tonight, somewhere slow and deep and far from the noise of ordinary life, then you have come to exactly the right place. Before we begin, if you enjoy these long, calm explorations of the ocean world, please consider liking this video and subscribing to the channel so that you never miss a new journey. It means more than you might think. And while you are settling in, finding a comfortable position, letting your breathing slow just a little, we would love to know where you are watching from tonight. Are you somewhere near the coast, perhaps close enough to hear the sea if you opened a window? Or somewhere far inland in a city or a quiet town with the ocean existing only as a memory or an idea? Wherever you are, the ocean is not far from your mind tonight, because tonight we are going to explore something that most people have never thought about. Something that happens constantly, right now, in the darkness beneath the ocean's surface. Something invisible and ancient, and in its own way, deeply beautiful. Tonight we are going to follow sound. Not sound as you know it on land, not the sound of voices or traffic or music. We are going to follow sound into the water. We are going to trace it from the moment it enters the ocean, through the strange physics that reshape it, down into the deep channel where it can travel without fadding for thousands of miles, past the Navy's secret listening stations, into the songs of whales crossing entire ocean basins, and finally to the edges of the unexplained. To sounds recorded in the deep ocean that no one has ever fully accounted for. Sound in the ocean is not a simple thing. It bends, it accelerates and slows. It finds pathways through the water that allow it to travel farther and more efficiently than sound travels through air. The ocean is not silent. It is in many ways one of the loudest environments on Earth, and it is full of information if you know how to listen. So let your eyes close if they want to, let your body settle, and come with us slowly into the water. To understand how sound moves through the ocean, it helps to start with what sound actually is. Not in a complicated way, just quietly, carefully, in the way that a long night of thinking naturally tends toward. Sound is movement, not the movement of objects through space, but the movement of energy through a material. When something vibrates, it pushes against the material surrounding it. That material, whether it is air or water or wood or stone, is made of particles. The vibrating object pushes those particles together, creating a small region of higher pressure. Then it pulls back, leaving a region of slightly lower pressure behind. That alternating pulse of compression and release travels outward from the source in all directions, moving through the material like a slow ripple moving outward from a stone dropped into still water. That traveling pulse is sound. On land, the material sound moves through is usually air. Air is a gas, and gas particles are relatively far apart, weakly connected to each other, and not particularly good at passing disturbances along quickly. Sound travels through air at roughly 340 meters per second at sea level. That is fast by human standards. It is fast enough that when you clap your hands, the sound reaches your ears essentially instantly, with no perceptible delay. But it is slow by the standards of other materials. Water is different. Water is a liquid. Its particles are much more closely packed than those of air. They are connected to each other by stronger forces. When one water particle is pushed, it pushes the next one much more efficiently than air particles push each other. The result is that sound travels through water roughly 4.5 times faster than it travels through air. In seawater at typical ocean temperatures, sound moves at approximately 1,500 meters per second. In some conditions, it moves faster still. This is the first of many surprising facts about underwater sound. When you imagine sound traveling through water, you might instinctively imagine it moving slowly, sluggishly, the way everything seems to move slowly in water when you watch objects sink or currents flow. But in reality, the opposite is true. Sound races through water. It is one of the fastest things in the ocean. The reason this matters is not just academic. The speed of sound determines how useful it is as a means of sensing the world. Bats use sound to navigate in air, emitting pulses and listening for the echoes. Dolphins and other toothed whales do something equivalent in water, and the faster speed of sound in water means that the information comes back more quickly, allowing for finer spatial resolution and faster reaction times. The physics of the medium is not incidental to the behavior of the animals that live in it. It shapes them over millions of years of evolution. But the speed of sound in the ocean is not constant. This is where things become genuinely interesting. The speed at which sound travels through seawater depends on three properties of the water: its temperature, its salinity, and the pressure acting on it. And in the ocean, all three of these properties change with depth. Not always predictably, not always smoothly, but they change. And as they change, so does the speed of sound. And as the speed changes, the direction of the sound changes too. This last point is the key to almost everything that follows. Sound does not travel in straight lines through the ocean. It bends, it curves. It is deflected by changes in speed, the way light is deflected when it passes from air into glass. The ocean is not a uniform medium through which sound passes unchanged. It is a layered, complex, three-dimensional landscape that sculpts sound into shapes and paths that seem almost deliberate, almost designed, but are simply the outcome of physics operating across enormous scales of space and time. To understand how and why sound bends in the ocean, we need to think about what happens at the surface, and then what happens as we go deeper. The ocean is not the same from top to bottom. Anyone who has ever swum in the sea and kicked down a few meters will have noticed the sudden chill that seems to appear out of nowhere. The surface is warm, sunlit, mixed by wind and waves, but below that mixed layer, the temperature drops. Sometimes it drops gradually. Sometimes it drops in a sudden, sharp transition that feels almost like crossing a boundary between two different worlds. This temperature structure is one of the defining features of the ocean, and it has a profound effect on how sound behaves within it. Near the surface, in what oceanographers call the surface mixed layer, the water temperature is relatively high and relatively uniform. Wind and wave action mix the upper ocean constantly, preventing strong temperature gradients from developing. In tropical regions, this mixed layer might be warm, 25 or even 30 degrees Celsius, and might extend down to 100 meters or more. In polar regions, the surface layer is much colder, and the distinction between surface and deep water is less pronounced. Below the mixed layer, the temperature begins to fall. This zone of falling temperature is called the thermocline. In the thermocline, the water that was warm at the surface transitions to the cold water of the deep ocean. The transition can be gradual, spread over hundreds of meters, or it can be abrupt, a matter of just a few tens of meters in which the temperature drops by 10 or 15 degrees. Now recall that the speed of sound in water depends on temperature, among other things. Warmer water conducts sound faster than colder water when other factors are held equal. So as you descend through the thermocline into progressively colder water, the speed of sound decreases. Sound moves more slowly in the cold deep water than it does in the warm surface water. This change in speed has a consequence that follows from a principle called Snell's law, the same principle that governs how light bends when it moves between materials of different optical density. When a wave moves from a region where it travels fast into a region where it travels slower, it bends toward a direction perpendicular to the boundary. When it moves from slow to fast, it bends away from that perpendicular direction. Applied to sound in the ocean, sound moving downward from the warm surface layer into the cold thermocline slows down and bends. It curves. Sound that begins traveling at a slight downward angle finds its path curving more and more steeply downward as it enters colder and colder water, as if the ocean is pulling it down. In shallow water. This downward refraction means that sound produced near the surface tends to curve away from the surface and dive into the depths. This creates what is sometimes called the shadow zone, a region just below the surface layer where sound from the surface does not easily penetrate. Ships trying to detect submarines using sonar have long understood this. A submarine that dives below the thermocline can effectively hide in the acoustic shadow, shielded from surface sonar by the refracting properties of the water column above it. But the story does not end at the thermocline. Because below the thermocline in the cold, deep ocean, something else begins to happen. As you descend into the deep ocean, the temperature continues to fall for a while, but eventually it levels off. In the deep ocean below the thermocline, the water is uniformly cold, typically between 2 and 4 degrees Celsius, sometimes less. Temperature is no longer changing much with depth. But pressure is. Every 10 meters of depth adds roughly 1 additional atmosphere of pressure. At 1,000 meters, the pressure is about 100 atmospheres. At 4,000 meters, it is around 400 atmospheres. At the bottom of the deepest ocean trenches, the pressure exceeds 1,000 atmospheres. And pressure, it turns out, also affects the speed of sound. Unlike temperature, which slows sound as it falls, increasing pressure increases the speed of sound. The water molecules are being compressed by the weight of the water above them, held more tightly together, and this allows them to transmit vibrations more efficiently. As you go deeper into the cold, high-pressure deep ocean, even though the temperature is no longer falling, the speed of sound begins to increase again, driven upward by the rising pressure. This means that somewhere in the middle of the ocean water column, there is a depth at which the speed of sound reaches a minimum. Above this depth, the water is warmer, so sound moves faster. Below this depth, the water is under greater pressure, so sound also moves faster. But right at this particular depth, the two effects balance each other out, and the speed of sound is at its lowest point. This depth of minimum sound speed is called the SOFAR channel. SOFAR stands for sound fixing and ranging. It was identified during the Second World War by American physicist Morris Ewing and geologist J. Lamar Wurzel, who recognized its extraordinary properties and understood immediately that it had significant strategic implications. The SOFAR channel is typically found at a depth of around 600 to 1,200 meters in the open ocean, though its exact depth varies with latitude and ocean basin. In tropical waters, it tends to be deeper. In polar waters, where the surface is already cold, it can rise almost to the surface itself. What makes the SOFAR channel so remarkable is what it does to sound. Sound that enters the SOFAR channel, that is, sound that is produced at or near the depth of minimum sound speed, undergoes something almost magical. Because the speed of sound is higher both above and below this depth, any sound wave that strays upward or downward from the channel axis is refracted back toward it. The channel acts as a waveguide, trapping sound within it, preventing it from dispersing in all 3 dimensions. Normally, when sound travels through water, its energy spreads outward in all directions, diluting rapidly with distance. The intensity of sound follows what physicists call an inverse square law. If you double the distance from the source, the intensity of the sound falls to 1/4. Triple the distance and it falls to 1/9. This rapid dilution is why sounds become faint so quickly as you move away from them. But sound trapped in the SOFAR channel cannot spread in all 3 dimensions. It is confined to a horizontal layer. Its energy spreads outward in 2 dimensions rather than 3. Instead of following the inverse square law, it follows a much gentler inverse relationship. Double the distance and the intensity falls only to 1/2. Triple the distance and it falls to 1/3. This seemingly small mathematical difference has an enormous practical consequence. Sound in the SOFAR channel can travel astonishing distances, not just kilometers, but thousands of kilometers, tens of thousands of kilometers. A sound produced in the SOFAR channel off the coast of Australia can, under the right conditions, be detected by a receiver in the SOFAR channel in the North Atlantic Ocean, on the other side of the world. The ocean, in other words, has a telephone network built into it, a natural acoustic waveguide that encircles the entire planet, allowing sound to travel from one side of an ocean basin to the other without any amplification, without any technology, simply by following the laws of physics through a layer of cold, pressurized water at middling depth. This was not known until the 1940s, and once it was known, it changed everything about how nations thought about the ocean. The Second World War made the strategic importance of the ocean impossible to ignore. Submarines had demonstrated that control of the seas required control of the underwater domain. Navies needed to know where enemy submarines were. And in the years following the war, as the Cold War deepened and Soviet submarine fleets expanded, the United States Navy found itself facing a problem that seemed almost impossible to solve. The ocean is enormous, submarines are small, they are designed to be silent, and they operate in 3 dimensions at depths where no aircraft or surface ship can easily detect them. Tracking them seemed at first consideration like trying to find a whisper in a rainstorm. But then came the SOFAR channel. Beginning in the late 1940s and through the 1950s, the United States Navy developed a classified system called SOSUS, the Sound Surveillance System. The idea was straightforward in principle, even if its execution required extraordinary engineering effort. Arrays of hydrophones, which are underwater microphones, would be placed on the seafloor at locations chosen to take maximum advantage of the SOFAR channel. These hydrophones would listen continuously to the sounds traveling through the deep sound channel. Signals from each array would be transmitted by cable to shore-based listening stations, where trained analysts would examine them for the acoustic signatures of Soviet submarines. The construction of SOSUS was a massive undertaking. Cables were laid across the floor of the Atlantic and Pacific Oceans, connecting seafloor hydrophone arrays to shore stations in the United States, Canada, Iceland, the Azores, Bermuda, and other locations chosen to provide overlapping coverage of the major ocean basins. The whole system was classified at the highest levels. The existence of SOSUS was not publicly acknowledged for decades. In practice, SOSUS proved extraordinarily effective. The SOFAR channel carried the sounds of distant submarines across thousands of miles of ocean to the waiting hydrophones. The low-frequency sounds produced by submarine engines and propellers, the very low-frequency sounds that traveled most efficiently through the deep sound channel, could be detected at ranges that would have seemed impossible without an understanding of the channel's properties. Each submarine had an acoustic signature, a characteristic pattern of sounds determined by the design of its propellers, the rhythm of its engines, the particular resonances of its hull. Experienced analysts could identify not just the class of submarine, but sometimes the specific vessel from its acoustic signature, the way an experienced musician can identify a particular instrument, or even a particular player from the quality of its sound. During the Cold War, SOSUS gave the United States Navy a profound strategic advantage. Soviet submarines transiting from their bases in the Barents Sea or the Pacific coast of Siberia into the open ocean were tracked as they passed through the acoustic coverage zones of the SOSUS network. Their positions could be estimated, their routes could be monitored. The ocean, which had seemed to offer Soviet submarines unlimited room to hide, turned out to have listening ears embedded in its floor. The Soviets were aware that the Americans had some kind of ocean surveillance capability, but they did not know precisely how it worked or how effective it was. The secrecy surrounding SOSUS was maintained with impressive discipline for many years. It was not until after the end of the Cold War in the early 1990s that the existence and general nature of the system were declassified and made public. When SOSUS was finally revealed to the scientific community, oceanographers and marine biologists realized that the Navy had, inadvertently, been building one of the most extraordinary tools for ocean research ever conceived. A global network of sensitive hydrophones, positioned to detect sounds at ranges of thousands of kilometers, capable of picking up not just submarines, but everything else that the ocean carried in the SOFAR channel. The sounds of distant earthquakes, the rumble of underwater volcanoes, the cracking of ice sheets in polar regions, the movements of large ocean currents, and something else, something that had not been expected at all. The songs of whales. In 1967, a bioacoustician named Roger Payne received a tape recording from a Navy underwater sound analyst named Frank Watlington. Watlington had been working with SOSUS-related hydrophone equipment in the waters around Bermuda, and he had recorded something strange. Long, complex, repeating sequences of sound. They were unlike anything produced by ships or submarines or known geological sources. They were clearly biological. And they were coming from humpback whales. Payne and his colleague Scott McVeigh analyzed the recordings carefully. What they found overturned the assumption, held almost universally at the time, that large whales were not vocal animals in any complex sense. The sounds on the tape were not simple grunts or clicks. They were organized, they had structure, they had recurring themes that were modified and repeated over the course of hours. They were, by any reasonable analysis, songs. In 1971, Payne and McVeigh published a paper in the journal Science describing the songs of humpback whales. It became one of the most influential papers in the history of marine biology. And in 1970, Payne had released a recording of humpback whale songs as a commercial album, which sold hundreds of thousands of copies and introduced millions of people around the world to the sound of the deep ocean for the first time. The effect was profound. The image of whales shifted in public consciousness. These were not simply large, commercially useful animals. They were complex, communicating beings producing sounds of extraordinary beauty and sophistication from the depths of the ocean. Humpback whales are perhaps the most famous singers in the ocean, but they are far from the only ones. Blue whales, the largest animals that have ever existed on Earth, produce calls of extraordinary intensity at very low frequencies. The calls of blue whales are typically in the range of 10 to 40 Hz, which is at or below the lower limit of human hearing. You cannot hear a blue whale call in the normal sense. You feel it. The calls are produced at sound pressure levels that make them among the loudest biological sounds ever measured. A blue whale call can reach 180 decibels or more, which is louder than a jet engine at close range. And because blue whale calls are at such low frequencies, with such long wavelengths, they travel exceptionally well through the SOFAR channel. Low-frequency sounds are absorbed less quickly by water than high-frequency sounds. They scatter less from the irregular features of the seafloor. They propagate through the deep sound channel with remarkable efficiency. A blue whale call produced in the SOFAR channel can be detected by sensitive hydrophones at distances of hundreds of kilometers. Under particularly favorable conditions, some researchers believe that the calls of the loudest whales may have propagated across entire ocean basins before humans altered the acoustic environment of the ocean. A blue whale singing in the South Atlantic might once have been heard by blue whales in the North Atlantic, thousands of miles away. We cannot know for certain whether this happened because we cannot ask the whales what they hear, but the physics of the SOFAR channel makes it plausible. And it raises a strange, affecting thought, that for millions of years before any human being looked at the ocean or wondered what lay beneath it, the deep sea was filled with voices crossing entire ocean basins, traveling in the waveguide of the deep sound channel, connecting animals separated by distances that would have seemed unimaginable to any early human standing on a beach. Humpback whale songs are particularly striking in their complexity and their changeability. Each population of humpback whales sings the same song at any given time, but the song changes continuously over the course of a breeding season. New elements appear. Old elements are modified or dropped. The changes propagate through a population remarkably rapidly, so that within months, all the males in a population are singing the latest version of the song. What is even more remarkable is that these changes can propagate between populations. Researchers studying humpback whale populations in the Pacific Ocean found that song elements appearing in populations off the Australian coast would, over successive years, spread westward through the Indian Ocean and into other Pacific populations, as if the songs were traveling cultural artifacts, moving through communities of whales the way a melody might move through human populations over time. Male humpback whales are the singers. They sing during the breeding season, hovering nearly motionless in the water, their enormous bodies perfectly still, producing sounds that travel through the ocean for kilometers around them. The function of the songs is not completely understood. They likely play a role in attracting females and in establishing relationships between competing males. But the songs are too complex, too structured, and too variable to be explained entirely by simple mate attraction signaling. There is something in them that seems to exceed the minimum requirements of their biological purpose. This is perhaps the most extraordinary aspect of whale song, not just that it exists, but that it is so much more than it needs to be. Humpback whales are not the only marine mammals using sound in remarkable ways. Among the toothed whales, a group that includes dolphins, sperm whales, orcas, and narwhals, sound is not merely a means of communication. It is a sense. It is a way of seeing the world in darkness and murky water. Toothed whales have developed a biological sonar system, usually called biosonar or echolocation, that allows them to perceive their surroundings through sound in extraordinary detail. The principle is simple. Produce a sound, listen for the echo, interpret what the echo tells you about what it reflected from. But the execution, refined over millions of years of evolution, is anything but simple. Dolphins produce their echolocation clicks in a specialized structure near their blowhole, involving a complex arrangement of nasal sacs and muscles. The clicks are extremely brief, measured in microseconds, and are produced at frequencies that can range from a few kilohertz to well above 100 kilohertz, far beyond the range of human hearing. These high-frequency clicks have short wavelengths, and short wavelengths allow for fine spatial resolution. The shorter the wavelength relative to an object, the more detail the reflected echo can carry about that object's shape, texture, and density. The sound is focused and projected forward through a remarkable structure in the dolphin's forehead called the melon. The melon is a rounded mass of fatty tissue with acoustic properties that allow it to act as an acoustic lens, shaping and directing the outgoing click into a focused beam that the dolphin can aim by slight movements of its head. The returning echoes are received not through the dolphin's small external ear openings, which are largely vestigial, but through the lower jaw. The fatty tissue of the lower jaw conducts sound vibrations inward to the inner ear with remarkable efficiency. Dolphins hear with their jaws. The processing power required to interpret echolocation returns is considerable. The dolphin's brain has devoted significant neural real estate to acoustic processing, and trained dolphins can distinguish objects that differ in size by just a few millimeters at ranges of many meters. They can detect a metal sphere the size of a golf ball at a distance of more than 100 meters. They can identify objects by their internal structure, not just their surface, because the echoes carry information about how sound waves penetrate and reflect within an object, depending on its material composition. There is a famous experiment in which blindfolded dolphins were able to detect the difference between hollow and solid metal cylinders of the same external dimensions at a distance of several meters. They were essentially performing ultrasonic imaging, a process we associate with medical technology, using nothing but their biological acoustic systems. Sperm whales take echolocation to a different scale entirely. Sperm whales are the largest of the toothed whales, reaching lengths of 18 meters in the case of the largest males. They dive to extraordinary depths in search of their primary prey, the giant squid. Descending to more than 1,000 meters, and sometimes deeper, holding their breath for 90 minutes or more. At those depths, in complete darkness, with no light at all, the sperm whale hunts by sound. The clicks it produces are among the loudest sounds produced by any animal on Earth, reaching levels of around 230 decibels. The acoustic organ that produces these sounds, called the spermaceti organ after the waxy substance it contains, occupies much of the whale's enormous rectangular head, which makes up roughly a third of the animal's total body length. The spermaceti organ appears to focus and amplify the clicks by bouncing them between two reflective surfaces within the head, producing a directional beam of enormous intensity. The echoes returning from the giant squid and other objects in the dark water allow the whale to navigate and hunt in conditions where eyes are entirely useless. The deep ocean, then, is not silent even in its darkest and most remote regions. It is filled with the clicking of sperm whales hunting, with the calls of blue whales traveling across ocean basins, with the songs of humpbacks echoing through warm tropical water. It is an acoustic environment of extraordinary richness, largely invisible to human senses, but perfectly legible to the animals that depend on it. The ocean is full of sound from many sources, not only biological ones. To understand the acoustic environment that marine animals navigate, it helps to think about all the layers of sound that fill the ocean at any given moment. At the very lowest frequencies, below about 10 Hz, the ocean carries the sound of the Earth itself. Earthquakes, both large and small, produce acoustic energy that travels through the ocean as well as through rock and sediment. The cracking and grinding of tectonic plates, the rumbling of underwater volcanoes, the collapse of ice shelves in polar regions, all of these contribute to a deep, infrasonic background that is the geological voice of the planet. Slightly higher in frequency, in the range from about 1 to a few hundred hertz, is a background of ocean noise that has its own name in ocean acoustics: ambient noise. In this frequency range, much of the background sound in the ocean comes from the interaction of ocean waves with each other. When two wave systems of slightly different frequencies cross, they create secondary pressure variations that travel downward into the ocean as sound. This process generates a nearly continuous, nearly global hiss of low-frequency sound that permeates the world ocean. This sound, called microseismic noise or ocean ambient noise, was identified and characterized in the mid-20th century. It is genuinely global. At any point in the open ocean, a hydrophone lowered into the water will detect this background. It is the sound of the ocean talking to itself, the acoustic product of the endless interaction of waves on every sea surface on Earth. In a higher frequency range still, from a few hundred hertz upward, additional sources of ambient noise become important. Rain falling on the ocean surface produces a characteristic hiss that is detectable underwater and that experienced oceanographers can use to estimate rainfall rates over the open ocean from hydrophone data. Wind-driven waves produce sound by breaking and by generating bubbles that oscillate as they are swept downward. Ships produce broadband noise from their engines and propellers, and the sound of distant shipping, even at ranges of hundreds or thousands of kilometers, contributes to the background noise level in much of the world ocean. The biological contributions to ocean ambient noise are substantial. Snapping shrimp, which are small crustaceans found in warm, shallow waters around the world, produce an almost continuous crackling sound by rapidly closing a specialized claw. The cavitation bubble produced by the closing claw collapses with a sharp snap that is audible many meters away. In areas where snapping shrimp are abundant, the combined sound of millions of snapping claws produces a loud, continuous crackling that can be heard through the hull of a ship, and that dominated acoustic surveys of shallow tropical waters before its source was identified. Snapping shrimp are thought to be one of the dominant sources of ambient noise in many shallow ocean environments. Fish also contribute to ocean ambient noise. Many species of fish are vocal, producing sounds through the vibration of their swim bladder, a gas-filled organ used primarily for buoyancy control. Toadfish, croakers, drums, and many other species produce mating calls, territorial sounds, and alarm signals by contracting muscles attached to their swim bladders. In coastal waters during spawning season, the combined sound of thousands of calling fish can be extraordinarily loud. There are records of the sound of spawning fish being heard through the hulls of anchored boats, mistaken by passengers for machinery or engine noise. The ocean floor itself is a complex acoustic surface. Hard rock reflects sound efficiently, soft sediment absorbs it, irregular terrain scatters it. The acoustic characteristics of the seafloor influence how sound propagates over long distances, because sound that travels at a shallow angle eventually reaches the bottom and must either be reflected or absorbed. The nature of the bottom determines how much energy survives each reflection. Mid-ocean ridges, the volcanic mountain chains that run along the centers of the ocean basins, are particularly complex acoustic environments. The rough, irregular terrain of a mid-ocean ridge scatters sound in many directions. The hydrothermal vents that occur along ridges produce broadband acoustic noise from the turbulent flow of superheated water. The geological activity of the ridges generates small earthquakes, called microearthquakes, that add to the acoustic background. In shallow coastal waters, the acoustic environment is different again. Tidal currents produce sound as they flow over irregular bottom features. River outflows carry sediment that scatters sound. Human activity, shipping, harbor construction, recreational boating, adds noise that drowns out biological signals. The acoustic environment of a busy coastal harbor is, from the perspective of an animal trying to communicate or navigate by sound, something like trying to hold a conversation at a crowded party while someone runs a jackhammer in the next room. The ocean has never been quiet. It has always been full of geological sound, biological sound, the sound of weather and waves. But the acoustic environment of the ocean has changed profoundly over the past century, and the change has been almost entirely one-directional. It has become louder. The primary driver of this increase in ocean noise is shipping. The global merchant fleet is enormous. There are tens of thousands of large commercial vessels on the world's oceans at any given moment, each one producing continuous broadband noise from its engines, and particularly from its propellers. Propellers produce noise through two mechanisms: direct mechanical vibration transmitted through the hull into the water, and cavitation, the formation and collapse of tiny bubbles in the low-pressure regions created by the spinning propeller blades. Cavitation produces a broadband hissing and crackling that is a major component of ship noise. Between the 1950s and the early 2000s, the volume of global shipping approximately doubled every decade as world trade expanded. The noise introduced into the ocean by this expanding fleet increased the background noise level across the low-frequency range by an estimated 10 to 20 decibels over this period. A 10 decibel increase corresponds, in the logarithmic scale used to measure sound, to a tenfold increase in acoustic power. 20 decibels corresponds to a hundredfold increase. For animals that rely on low-frequency sound to communicate across long distances, this increase in background noise has direct consequences. The range over which a blue whale call can be detected above the background noise depends on how loud the call is relative to the background. As the background rises, the detectable range falls. Researchers studying this question have estimated that the effective communication range of blue whales may have been reduced by as much as 90% compared to what it was before the era of industrialized shipping. A call that might once have been detectable at a range of 1,000 kilometers may now be audible only to 100 kilometers. This is not a slow, gradual change. It happened over the course of a few human generations, which is almost instantaneously on the timescale of whale evolution. Animals whose communication systems evolved over millions of years in a much quieter ocean are now operating in a profoundly altered acoustic landscape. The consequences are not fully understood. Whales do not leave records. We cannot go back and measure how blue whale populations communicated in the 1850s, before steamships became common on the ocean. But there are lines of evidence that suggest the noise increase matters. Studies of humpback whale singing have found that whales in areas with higher shipping noise tend to sing at lower frequencies, which carry better through the noise and at louder volumes. Some species have shifted the frequency of their calls over time in ways that parallel the increase in low-frequency shipping noise. Whether these are genuine adaptations, heritable changes driven by selection pressure, or simply flexible adjustments made by individual animals in response to immediate acoustic conditions, is not always clear. Military sonar has also attracted significant attention as a source of potentially harmful acoustic energy in the ocean. Military active sonar systems, particularly mid-frequency sonar used for submarine detection, produce intense pulses of sound that can be heard at ranges of many tens of kilometers. there is substantial evidence that these sonar pulses can disturb cetaceans severely. Mass strandings of beaked whales have occurred in temporal and spatial association with naval exercises involving active sonar in multiple locations around the world. Necropsies of stranded beaked whales have found gas bubble lesions in their tissues, similar to the decompression sickness that affects human divers when they ascend too quickly. One hypothesis is that the intense sonar pulses cause panicked whales to surface too rapidly, or to alter their diving behavior in ways that induce bubble formation. Another is that the sound directly causes acoustic trauma. The precise mechanism remains debated, but the association between naval sonar and beaked whale strandings is now considered well established by the scientific community. Seismic surveys, used by the oil and gas industry to map geological structures beneath the seafloor, produce extremely loud, low-frequency pulses at regular intervals using devices called airguns. An airgun survey vessel tows arrays of airguns that fire simultaneously every few seconds, producing impulses that can exceed 250 decibels at the source. These pulses penetrate the seafloor and reflect back from geological layers at different depths, providing information about subsurface structure. They also propagate through the water column for hundreds of kilometers, adding periodic intense pulses to the ambient noise environment. The response of marine animals to seismic surveys has been studied extensively. Whales tend to move away from areas of active seismic surveying. Fish may show startle responses and altered behavior. There is evidence that the larval stages of some marine invertebrates are damaged by exposure to intense acoustic pulses. The fisheries implications of widespread seismic surveying in productive ocean regions are not fully understood. There is now a growing field of ocean noise management, in which the acoustic impacts of human activities are considered alongside other environmental factors when permits are issued and regulations are written. Some approaches to reducing shipping noise focus on propeller design, since quieter propellers reduce cavitation noise substantially. Reduced vessel speed is also effective, as propeller noise increases steeply with speed. Some ports have begun implementing slow-speed zones for incoming vessels in sensitive marine areas, with measurable reductions in local noise levels. The ocean is not yet quiet again. The challenges of reducing the acoustic footprint of global shipping and other marine industries are immense, but the awareness that the ocean has an acoustic environment worth protecting, that the sounds of that environment matter to the animals within it, has grown considerably over the past 2 decades. The ocean is not merely a resource to be extracted from and a surface to be crossed. It is a place with its own complex sensory world, its own voices, its own conversations happening at depths and distances that dwarf anything in human experience. The ocean keeps secrets. Despite everything that science has learned about underwater sound, its physics, its biology, its military and industrial dimensions, there remain sounds recorded in the deep ocean that have never been fully explained. Some were eventually identified, their mystery resolved by patient investigation. Others remain open questions, sounds that entered hydrophone recordings and left again without offering a clear account of their origin. Perhaps the most famous of these is the bloop. In 1997, instruments operated by the National Oceanic and Atmospheric Administration, monitoring the Pacific Ocean for earthquake activity, recorded an unusual sound. It was loud, extremely loud, loud enough to be detected simultaneously by hydrophones separated by thousands of miles of ocean. It rose rapidly in frequency over about a minute, from a very low pitch to a slightly higher pitch before fading. The sound was given the informal name the bloop by the scientists who analyzed it. The bloop attracted immediate attention, not least because its characteristics did not obviously match any known geological or biological source. It was too loud for most biological explanations and did not match the signatures of known seismic events. For a period, it became the subject of considerable public speculation. including suggestions that it might represent an unknown enormous creature in the deep ocean, something larger than any known animal, given that only a very large biological source could produce such intensity. Scientists eventually reached a consensus that the bloop was likely the sound of a very large iceberg cracking and fracturing on the seafloor or against an underwater ridge somewhere in the southern Pacific Ocean. Icequakes, as these events are sometimes called, can produce broadband sound of enormous intensity, and the rising frequency character of the bloop is consistent with the acoustic signature of large-scale fracturing ice. The area of the southern Pacific where the bloop appeared to originate is consistent with known regions of iceberg activity. But the consensus came gradually, and the explanation is not universally considered definitive. The bloop remains an example of how much remains uncertain about the acoustic environment of the deep ocean. Other unexplained sounds have followed similar trajectories: initial mystery, scientific investigation, tentative explanation. The train, the Julia, the slow down, the upsweep, all of these are sounds recorded on NOAA's hydrophone network that were given informal names by the scientists who noticed them. Some were eventually attributed to known geological processes. The upsweep, a sound of slowly rising pitch first recorded in 1991 and continuing for years, is thought to originate from volcanic activity on a seamount in the southern Pacific. The slow down, a sound that descends slowly in frequency over about 7 minutes, is also considered likely to be geological in origin, perhaps related to ice or seafloor processes. But the ocean is large, and the hydrophone network is sparse. There are certainly sounds occurring in the deep ocean that have never been recorded, or that have been recorded and not yet noticed amid the vast archive of acoustic data that accumulates continuously. There may be biological sources that have not been identified, animals or biological processes that produce sounds unlike anything currently in the reference library of marine bioacoustics. There is a precedent for this. Fin whale calls, which are extremely loud and extremely low in frequency, were recorded in oceanic hydrophone data for decades before they were identified as biological in origin. They were at first assumed to be geological noise. The idea that an animal could produce sounds of such intensity and such low frequency was not initially considered plausible. It took systematic investigation to connect the sounds to fin whales. The same principle might apply to other sounds. The ocean is dark and deep and vast, and we have been listening to it seriously for only a few decades. The archive of hydrophone recordings accumulated since SOSUS was first deployed, and since civilian monitoring systems were established, is enormous. The task of analyzing all of it, of finding patterns and anomalies and unexplained events in years of continuous recording from dozens of stations, is one that will occupy scientists for years to come. It is a humbling thought. The ocean carries sound from one side of the world to the other. It has been doing so for as long as there has been an ocean. The geological sounds of volcanoes and earthquakes have been traveling through the SOFAR channel for hundreds of millions of years. The biological sounds of animals have been in the ocean for as long as there have been animals capable of producing them, long before any human ear was there to hear them. We arrived recently and began to listen and found that the ocean was already full of voices. We have identified most of them. We think we cannot be entirely sure what we have missed. There is one story about underwater sound that deserves its own space, not because it involves mystery in the scientific sense, but because it has lodged itself in the imagination of people around the world in a way that very few facts about ocean acoustics have managed. In 1989, scientists at the Woods Hole Oceanographic Institution, analyzing data from the SOSUS network, noticed an unusual signal, a whale call, but unlike any whale call they had heard before. Most blue whale calls occur at frequencies between 10 and 40 Hz. Most fin whale calls occur around 20 Hz. The call they were hearing was at 52 Hz, still very low by the standards of most sounds, far below the normal range of human hearing, but dramatically higher than the calls of any known large baleen whale. And the call was clearly biological, with the rising and falling patterns and the structure of a purposeful signal, rather than a mechanical or geological source. Over subsequent years, the signal reappeared regularly, moving through the Pacific Ocean on paths consistent with the annual migrations of a baleen whale. It moved at speeds consistent with known whale species. It appeared alone, never accompanied by other animals of its kind, and it never seemed to receive a reply. The whale came to be known informally as the 52 Hertz whale, and later simply as the loneliest whale in the world, a name that says as much about the humans who gave it as about the animal itself. The narrative that attached to it was this: here was a whale calling at a frequency no other whale could hear, moving through the ocean on normal whale migration routes, calling and calling but receiving no response, because no other whale's ears were tuned to the frequency it was using. The science is more complicated. We do not know that no other whale can hear the 52 Hertz whale's calls. Whale hearing ranges are not perfectly understood, and it is possible that other whales could detect its calls even if they could not respond in kind. We do not know that the whale is alone. The SOSUS network, for all its sensitivity, cannot track every individual animal in the ocean simultaneously. The 52 Hertz whale may be a hybrid between two species, perhaps a blue whale and a fin whale, producing calls at an intermediate frequency that reflects its mixed heritage. It may be a blue whale with a physical abnormality affecting its vocalizations. It may be one of a small group of whales with unusual call frequencies that have gone undetected because the network was not specifically looking for them. The whale is probably not lonely in any meaningful sense. It probably does not experience loneliness. It is an animal, navigating the ocean by sound as its kind has always done, producing calls that serve whatever biological purpose calls serve. But the story persists because it speaks to something in human experience that the facts alone cannot quite explain away. The idea of a voice that reaches across an ocean but cannot find anyone listening is not a scientific finding. It is an image. And it is an image that resonates, perhaps because so many people have felt, at one point or another, something like that particular silence. The 52 Hertz whale is still out there. The signal has been detected as recently as the 2010s, though there is some evidence that the frequency has drifted slightly lower over time, possibly due to the animal aging, possibly for other reasons. It is still calling. It is still moving through the Pacific Ocean, following routes that look like migration routes, doing whatever it does, producing its unusual, distinctive voice in a frequency range all its own. We have been speaking all night about what we can learn from sound in the ocean, about the physics of how it travels, about the animals that use it, about the navies and scientists who have listened to it. But there is something broader here, something that sound in the ocean reveals about the ocean itself that goes beyond any particular application. The ocean is difficult to know. It covers most of the planet. Its deepest regions are inaccessible to direct observation. Its interior is opaque to light and to most of the electromagnetic spectrum. Most of the ocean cannot be seen, even from above. Satellites can see the surface. Submarines and ROVs can visit specific locations. But the vast interior of the ocean, the hundreds of millions of cubic kilometers of water between the surface and the seafloor, resists direct observation in a way that few environments on Earth do. Sound is different. Sound travels through water. It carries information from its source to wherever it can be detected. And the SOFAR channel means that sounds from one part of the ocean can be detected by instruments thousands of kilometers away. This makes sound, in principle, a tool for knowing the ocean at scales that no other method can reach. Oceanographers have used this insight to develop a method called acoustic thermometry, or ocean acoustic tomography. The idea is based on the fact that the speed of sound in water depends on temperature. If you know the distance between a sound source and a receiver very precisely, and you measure the travel time of a sound pulse very precisely, you can calculate the average speed of sound along the path. And if you know the average speed, you can infer the average temperature. If you have many sources and many receivers, arranged around a large ocean basin, you can reconstruct the three-dimensional temperature structure of the interior of the ocean, the way a medical CT scanner reconstructs the internal structure of a body from X-ray projections in many directions. The ocean becomes legible through its acoustics. This is not just an academic exercise. The temperature of the deep ocean matters enormously for understanding climate. The ocean stores enormous amounts of heat, and changes in the deep ocean's temperature distribution reflect global shifts in climate that are not easily measured any other way. Monitoring the ocean's heat content over time is essential for tracking how the climate is changing and how the ocean is responding. A project called the Heard Island Feasibility Test, carried out in 1991, demonstrated that sound produced near a small island in the Southern Ocean could be detected by receivers around the world, verifying that acoustic thermometry at global scales was physically feasible. Subsequent projects have used ocean acoustic tomography at regional scales to monitor ocean temperature changes in the North Pacific and other regions. Sound, in other words, is not only something the ocean carries, it is something the ocean can be known through. It is a means of sensing an environment that resists almost every other kind of sensing. The acoustic properties of the ocean, which evolved as a background condition within which marine animals developed their vocal and auditory systems, have turned out to be a window through which human science can peer into the interior of the planet's most important and least understood environment. It is late now, or perhaps early, depending on where you are and what time your eyes found this video. The ocean is still out there, as it always is. Its surface is moving, somewhere in patterns of waves driven by winds that began as differentials in air pressure, driven ultimately by the uneven heating of the planet by the sun. Below the surface, the water is stratified, warm above and cold below, separated by the thermocline. And somewhere in the middle depths, around 600 to 1200 meters down depending on the ocean basin and the latitude, the SOFAR channel is doing what it always does. Right now, as you read these words or hear them spoken, sound is traveling through that channel. Some of it is the sound of ships, the broadband mechanical noise of steel hulls and turning propellers, crossing from continent to continent on the same invisible paths that have carried trade for centuries. Some of it is geological, the distant rumble of a small earthquake on a mid-ocean ridge somewhere, a crack in the Earth's crust releasing a little of the heat that has been accumulating since the planet formed. And some of it is biological. Right now, somewhere in the Pacific Ocean, a blue whale is calling. The call is at a frequency below what you can hear, lower than any note on a piano, a deep, slow vibration of enormous power. The call enters the SOFAR channel and travels. It travels north and south and east and west, diminishing but not vanishing, following the curved paths that the physics of the ocean imposes on it. How far it will travel before it fades below the threshold of detection depends on the noise in the channel, on the particular configuration of temperatures and pressures in the water column tonight, on countless small factors that no one is calculating. It might be detectable for 100 kilometers. It might be detectable for 500. Under the right conditions, in the right part of the ocean, it might carry for 1,000 kilometers or more, a living voice crossing the span of ocean basins, carrying information, or carrying something that serves the function of information, across a medium that has been carrying sound since long before any living thing had the capacity to hear it. The ocean is very old. Sound has been moving through it for a very long time. The SOFAR channel existed before there were whales, before there were fish, before there were animals at all. The physics of it required only that there be water and temperature and pressure and the curve of the Earth's crust. All of that was in place for hundreds of millions of years before evolution produced an animal complex enough to make use of it. It is a quiet thought, perhaps a good one to let yourself settle into as you drift towards sleep. The ocean carries voices that have been traveling longer than anyone has been around to hear them. The laws of physics that route sound through the deep sound channel are the same laws that shape the behavior of every drop of water on Earth, that hold the oceans in their basins, that drive the currents that moderate the climate and carry nutrients from the deep to the surface and back again. We are part of a very large, very old, very interconnected system. The sound we have been following tonight is just one thread in it, one of the countless forms of energy moving through matter in ways that follow rules that have not changed since the universe was young. But it is a thread worth following. It leads to whale songs, and to secret Navy networks, and to the loneliest voice in the ocean, and to the first scientists who placed a microphone in the water and heard, for the first time, what the ocean had been saying all along. And with that, we have come to the end of our journey through the acoustic world of the ocean. From the surface layer where sound begins its descent, through the thermocline where it bends and curves, down into the SOFAR channel where it can travel for thousands of miles without fadding. We have listened alongside the Navy's SOSUS operators, standing watch over hydrophone recordings, looking for the acoustic fingerprints of distant submarines. We have heard the songs of humpback whales changing and spreading through populations across the Pacific. We have followed the echolocation clicks of dolphins as they painted pictures of the underwater world from returning echoes. We have sat with the unexplained sounds, the bloop, the upsweep, the others, and accepted that the ocean still has things it has not fully told us. And we have spent a moment with a single unusual voice, calling at 52 Hertz through an ocean that may or may not have been listening. The ocean is not quiet, it never has been, but its sounds are largely below the threshold of human hearing, propagating through a medium that humans cannot enter without technology, in a waveguide whose existence was not even discovered until the middle of the 20th century. The acoustic world of the ocean has been going on without us for longer than we can properly imagine. We are newcomers to the listening. Thank you for spending this time here. If this video was a good companion for sleep or for quiet thought, please like it and share it with someone who might appreciate a long, slow journey through one of the ocean's quieter secrets. And we will see you on the next exploration. Sleep well, the ocean is still out there, still carrying its voices across the dark water, still bending sound through the physics of temperature and pressure and depth, still, in its deep and ancient way, talking to itself across the spans of ocean that cover most of this world. Good night.